Yeah, so regarding this particular course, I'll be talking more about material point of view. Am I audible? Yeah, so it is like most of the talk is you say like it is related to modeling and modeling with respect to stress and all. But we'll be talking more about how materials behaves once we are applying the stress and particularly for ceramic material. Okay, so in ceramic material that too fatigue wear. So in that particular condition, actually, if you talk about this ceramic, as like okay for fatigue wear, progressive damage leads to development of some debris, and that debris actually lead to further fracture and wear of the material. And in case of ceramic, the most important point is they have been chosen because they are actually hard, at the same time they are wear resistance and core resistance. So that leads their application, they are very promising component, you can say promising element to use for that wear applications. Like these are the engineering application you see. So these applications are being like mostly if you see this is nozzle, this is heat exchanger tube, bearings, and then ballistic materials. So those all are the application where the ceramics are being used very frequently, considering their very high hardness. At the same time, they are corrosion resistance as well and wear resistance as well. So talking about wear mechanism for ceramic, it is like okay, it is in the same way like okay, crack initiation, crack propagation, and then it leads to fracture. So if you consider this point here, once you go for repetitive action, you will be having that crack getting initiated, and then it will try to get propagate, and that secondary crack will get generated and it will touch to the surface. This will see in actuality once we are analyzing the subsurface analysis, I will be letting you know. So then this complete part will come as a chunk, and then it will be get fractured. So usually in case of ceramic, this is what the pure that it is being considered as delamination. So it is like okay, complete surface is getting deformed, and then some like dislocation may occur, and then the cracks will get occurred, and this complete chunk will come out, and it will be considered as fractured part. Then fractured part will again become the crushed and all those things under the suppressive layer and all those things, and it will form a debris which can be supportive as well as destructive. So we'll see one by one, it comes in both the way. So in that part only Suh delamination theory has also come. It is like okay, if you go for the repetitive loading unloading condition, dislocation get generated, and this can get piled up because of hard inclusion or some other inclusions, okay, hard surfaces, and this will form a void, okay, because that continuously strain hardening phenomena will occur, that stress will actually try to release the energy, and then they will create two surfaces. Once they will create two surfaces, you can understand that whatever the energies are there, that will get released. So this is how they form the voids, and then these voids go to coalescence, and it will form a long crack which can get some connected with the surface cracks, and that complete chunks can come out. So this theory has been given by Suh. So it is being considered as Suh delamination theory, that we can see in this particular stage as well, where we are having primary, secondary, and fourth, like different cracks are getting generated, and actually they are getting connected to the surface, and it is coming out. So we can say like okay, different models have also been proposed for ceramic conditions, considering their absence of any layer. Like okay, usually when it is being proposed in case of ceramic, if you are forming some tribochemistry, there some tribo layers are there, then no models has been proposed yet, because that tribo layer can have different roles. But if you are considering pure mechanical fracture, in that particular condition, two models have been proposed. Once for like okay, sharp indenter, if you are considering, and another is for blunt indenter. Okay, like this type of indenter if you see. Okay, so in that particular condition, we can have different type of cracks being generated on the ceramic surface: lateral crack, median crack, radian crack, and conical crack. So one first model that is dependent on sharp indenter model is, it is being proposed by Evans and Marshall, where you can calculate the wear volume on the basis of their elastic modulus, hardness, load being applied, and K1. K1C means it is mode first, because if you consider for ceramic it is being fractured easily in tensile mode. So this is why once we are talking about ceramic, wear of ceramic, usually we consider like till now we are considering for K2C, because it is metal. Once you are considering for metal, they get easily shear off. Okay, so in shear mode they can they can get cut out easily. So this is why once you are considering for, you have to consider what type of material you are choosing. If you are considering for, let's say, metal, then you have to go for K2C. But if you are considering for ceramic, ceramic get easily fracture in tensile mode, K1C. So this is why once we are considering for wear volume for ceramic in sharp indenter mode, we are considering K1C, and the same model has been modified for blunt indenter by Tewari and all. So they have been considering like wear will be dependent on other factors as well, where if you go for fretting wear, so on that basis we will be having this conical crack being generated. Okay, this conical crack being generated on the surface, and then the material will come out completely a chunk, and you will be having fracture part. So important properties, key properties for ceramic, if you consider for fatigue wear application, that is high hardness you can consider. So they are having very high hardness considering their covalent bonding and ionic bonding. You can understand they will not allow to break easily. So they will be having high hardness. At the same time, brittle material, they are having brittleness like fracture toughness. So once you are talking about ceramic, in ceramic actually you are not, you will be having multiple of pores inside, which can be considered as let's say crack size, okay, and that could be of critical size and it will get fracture. So in case of ceramics, we are considering cracks are available. Now the cracks should not get propagate fast, okay. So once we are talking about ceramics, so we have to consider fracture toughness instead of toughness or other property, because we consider like cracks are always there, okay. Now these cracks, how fast it can propagate, we have to hinder that propagation of crack, okay. That is toughening mechanism we are trying, like toughening mechanism could be like, okay, transformation mode, and as well as you can go with the particulate or something like that. You see, like if you are having some crack being generated over the surface, let's say, okay. So if some cracks are being generated and how fast it can move, okay. So in case if you generate some if you are using some particulate or fibers, let's say, okay. So this is like second phase incorporation in the first phase. So this crack, once it is coming here, it will get breached by this particular particle. Let's say this particle is coming here, so it will get breached by this particular particle, and this crack will not be able to flow up to this particular extent, because the energy of the crack being absorbed by this particular particle, and it can go for up to here only if it is bridging. If it is crack deflection, this crack has to get deflected by like this, and then it has to go. So again, its energy is getting absorbed by traveling mode, okay. Like you are having fuel in your car, you can go up to your railway station, but if you are going with another route, like you cannot reach to your station. So the same way, like this crack is having some energy, but if it is getting deflected, it will not come up to here and it will not get parted, okay. At the same time, if it can get breached. Breach means this energy will get transferred in the atoms, and then again this energy is sufficient to break the another phase, but it is not able to, like this crack is floating, okay, and it is getting breached here, okay. So this surface is getting fractured, but this surface will not get fractured by this energy. So this energy will get transferred here, atomic level it is getting transferred to this side, again this surface will get fractured, but some energy will get absorbed by this particular atoms, or let's say particulate or some fiber element, okay. So this is how you can improve the toughness of this, like in case of if you go for ceramic, okay. So that is being considered toughening mechanism. Then they are having very high thermal stability, which is being very good if you go for aerospace applications or some tribological applications, critical temperature applications. Then porosity, as I told you, okay, they are already having some porosity, so that can get reduced by more let's say additives you use, different type of liquid phase sintering you go, or you can go for high pressure, high temperature conditions, okay. Then again factors that is affecting for fatigue wear in ceramics are covalent and ionic bonding. Again you can say like, okay, if you are having different like in case of metal, if you go, they are having more slip planes, but if you consider, let's say we are considering ionic ceramic, okay. So they are having plus minus, so they will be having ion are being actually oriented in this particular fashion. Then again minus, plus, minus. So this is how they are having, their atoms are being oriented. So if you try to see if you try to see any slip planes, if you consider one plane which is being you can consider as slip planes, let's say, okay, let's say this plane only we are considering as slip plane. To let the crack move, okay, let the dislocation move, that cracks should not get generated. What happens here is, as soon as you try to move this particular plane under this particular plane, what happens, this positive will try to come towards positive, which will repel, which will not attract. Okay. So, this is why the slip system actually in ceramics becomes less. Okay. They will not allow the dislocation to move, and then what happens, like, okay, they will generate crack. Okay. So, this will generate the crack and energy will get dissipated. So, this is why the covalent and ionic bonding, which is helping again in generation of brittleness as well, okay, apart from the hardness. Then it will be having low real contact area, as we are talking about asperity to asperity contact. Okay. If you go for metallic, this asperity contact will be more closer, but they are pores, they are hard enough. So, the actual area of contact will be less. Okay. So, actual area of contact will be less. So, in that case, whatever the adhesive we are considering, that will be less. Okay. So, in case of ceramic, again amount of adhesive wear will be less. Then if you consider asperity fracture interlocking, they might lead, because they are hard enough. So, they might lead for high friction condition, like just now Professor Mayank has shown, like, okay, they are having high friction if you are going for hard coating, but at the same time they are having low wear, because they are hard enough, wear is less, but they are hard enough and they are getting interlocked inside, friction will be more. So, friction could be higher, but at the same time, if your requirement is to reduce the wear, we can go for ceramic coating as well. Then you will be having like interaction between moisture and all those things, that also affects very drastically in case of if you go for ceramic. So, that I will cover the things here. So, and then factors which can influence, we already have talked about stress amplitude, loading frequency. Okay. So, I will be focusing more about grain size, reinforcing phases, additives, and then environment like humidity and temperature. So, my talk will be oriented towards here. We can see, like, okay, if you go for silicon carbide ceramics, it's like wear rate and coefficient of friction with humidity, it decreases drastically. So, in low layer ceramics are being considered as let us say corrosive resistance, but at the same time they are very prone for forming some particular layer which can protect the surface. Okay. So, we will see that we already have included few case studies. So, on that basis, actually I have selected two topics here. One will be understanding tribological behavior of silicon carbide tungsten carbide composite, where we will see the effect of sintering composition, like we will be having matrix of silicon carbide, which is having hardness about let us say 26 GPa, and will incorporate tungsten carbide particle from 0 like pure monolithic SiC to 50% tungsten carbide in weight percent, 10%, 20% to 50% will go. Then we will change the load, we will change the counter body configuration. Configuration means we will go for unidirectional continuous sliding as well as bidirectional reciprocating sliding. Then how the wear behavior changes, that we will also see, and then we will see the effect of humidity and temperature. So, in that particular condition, apart from the stress and all, we will also see how other factors are affecting your wear behavior or tribological performance. And then we will see the micro mechanism, that cracks generation and crack getting bridged, how dislocation pile up which actually generating the cracks, that we will also see here. Then we will see whether that sliding load and time actually affects the property, like, okay, tribological performance of silicon carbide ceramics. We will see the evolution of, actually here we will be trying to see evolution of our debris. Okay. If debris profile is changing, we can consider, like, okay, certainly our tribological performance will change. So, on that basis silicon carbide ceramics have been chosen. So, on where, because it is like, okay, very high hardness, as I told, excellent high thermal stability, strength stability, low thermal expansion, but they are having moderate fracture toughness. Okay. So, their fracture toughness, if you compare with the metal is having fracture toughness around 100, okay, and ceramics usually have less than 10. So silicon carbide is having fracture toughness 3 to 4.5. So though they are having very high hardness and all those things, wear resistant, but at the same time they are fracture. Once they get fracture, catastrophic failure will be there. It will not give you the indication to change the material. So in that particular condition, we need to improve the toughness. So to improve the toughness, we opted for tungsten carbide composite. Tungsten carbide incorporation. Why? If you go with the Young modulus value of silicon carbide and tungsten carbide, so they are having very huge difference. Like tungsten carbide is having around 700 megapascal gigapascal, and silicon carbide is having 400 gigapascal. So this difference is huge. Okay, so if you incorporate, however, hardness, if you see, tungsten carbide is having around 20 GPa, and again SiC is having 26 GPa. So if you incorporate tungsten carbide in silicon carbide, what happens here is, like, okay, we are considering like we'll be compromising with the hardness, but yes, we can have very high Young modulus, which is nothing but, if you go with the Einstein's formula, it gives you high fracture toughness. Okay. So in this particular condition, we opted for tungsten carbide to incorporate in silicon carbide. So this is the batch composition we started with. So like 0% tungsten carbide, that will be designated as HW0, 10% that is designated as HW10, 30% HW30, and 50%. This is weight percent. Okay, weight percent, and other additives are also there, but we are considering like, okay, we are mainly focusing on incorporation of tungsten carbide, how much amount is being placed. So if you see, like, this is being sintered, and we are getting more or less almost 98 to 99% density. So this is the batch composition that is being mixed. Okay, ball milled. This is how it get prepared, actually sintered. Powder metallurgy we have used, ball milled in ethanol for almost 24 hours. Then it is being dried and hot pressed at 1800 degrees Celsius in argon atmosphere for under 40 megapascal pressure for 1 hour, and we got this sample. So this is what the sample is. So etched microstructure. So first we have to analyze what like, okay, if you see with incorporation of tungsten carbide from 0 to 50% reduction in grain size, we can see reduction in grain size from 830 to 550 nanometer. So this reduction in grain size will give you very good property. We will see just now. First we will see the fracture toughness. So fracture surface we will also analyze. What we found, like, okay, if you go for monolithic SiC HW0, it is mainly intergranular fracture. If you see, it is like, if you see these particular points, okay, like complete grains are coming up. It is mostly dominated by intergranular fracture. But if you move towards HW50, if you see, this is slits. So it is transgranular. So transgranular fracture is getting, you say, like, okay, dominated with incorporation of tungsten carbide in SiC. Okay. So now if you see the different microstructural and mechanical property, if you analyze, so what we found, like, okay, with incorporation from 0 to 10 to 30 to 50, sinter density we got well, grain size is continuously decreasing. Okay, grain size is continuously decreasing, and hardness, what we thought, like, okay, will compromise with the hardness. So hardness, if you see, it is actually increasing up to 30, and then it got somewhat decreased. So very interestingly, reduction in grain size out of tungsten carbide is helping in improvement in hardness. Though we consider, like, with incorporation of tungsten carbide we will be having better fracture toughness, but at the same time we will compromise with the hardness of the material. But it is not the case, because the tungsten carbide is, during the sintering process, it is not allowing the grain to grow. Okay, and this helps in improvement in hardness as well. So we are getting benefit of high hardness as well as high fracture toughness with incorporation of tungsten carbide. So we got benefited by this. So how fracture toughness is getting improved, the same mechanism I was explaining. You see, cracks are not for HW0, it is almost the same line you see. Okay, but as you incorporate this tungsten carbide particles, they are getting bridged. These cracks are getting bridged, they are getting deflected, and this crack deflection and crack bridging actually helps in improving the fracture toughness. Okay, that we'll see again once we are realizing the level of, like, up to micro mechanism level. Okay, subsurface level. So then this sample has been subjected for, let's say, first unidirectional sliding, like continuous sliding. Okay, where to understand the different, like, counter body behavior. At the same time we will be seeing, like, here the at let's say atmospheric condition is our humidity is close to 25 plus minus 5%. So it is being considered as normal humid condition. Okay, it is not moderate, not high humid condition. Okay, so in this particular condition we are changing the load as well. So as we talked about, we'll see the effect of counter body and load and composition all together here. So first, for pure SiC, monolithic SiC, we are changing load. So what we found here is, if you go with different counter body, so if you see the counter body hardness here, so it is changing in multiple of 2, 7, 14 and 28 GPa. The counter body has been chosen in particular fashion, and at the same time it has been chosen in form of, this is metallic, this is cermet and this is ceramic. So how it will behave if you go for their frictional behavior. So if you see here, maximum COF, if you go for any particular load, maximum coefficient of friction, average coefficient of friction we are getting in case of cermet. Okay, it is not in case of silicon carbide, ceramic, or in case of steel. And if you see with increasing load, though at lower load steel is having in between, but with increasing load it is going to down. It is going to down for silicon carbide ceramic if you increase the load. We'll see the mechanism why it is happening. Okay. At the same time, if you go for, like, this is the surface profile we got against all for with change of 10, 5, 10, 20 Newton, and we use this particular formula. Simply we are measuring the depth in between and W, and we are going for 2 pi r d into W to calculate the volume. We did not go with the area under the curve. We use the simple method. Okay. It is already being considered like applicable for different in different applications. Okay. So we can consider this particular method to use the wear volume. So this is what we found, average COF if you see with respect to, if you go for tungsten carbide composition now. So the earlier one is with respect to simply monolithic SiC with respect to load. Okay. Now we will see how with the composition friction is changing. That we will see only at 20 Newton load. We are not looking at 5, 10 Newton load. We are going for 20 Newton load. What we found here is, for SiC, like yesterday Professor Nelius was saying, if you go with the matrix is hard and your inclusions are particles you are including is, that is softer, friction will reduce. This is what we are seeing in case of silicon carbide with respect to against the silicon carbide wall, against the tungsten carbide wall, it is continuously decreasing. But very interestingly, if you go for steel, it with respect to incorporation of tungsten carbide particle, more number of tungsten carbide particle, it is actually increasing. Okay. So we have to see, like, okay, as per theory it should decrease because we are incorporating more number of softer phase in matrix. Okay. So this is decreasing for all condition, but it is very interestingly it is increasing for, if you go for metallic body, silicon carbide body. Okay. Sorry, steel body. So wear is, yeah, with increasing load it is increasing for SiC as well as it is increasing for, it is decreasing for with incorporation of tungsten carbide, because we have improved hardness, we have improved fracture toughness. So that is leading to decrease in continuously wear with incorporation of tungsten carbide, and with increasing the load we already have seen the profile. So wear is continuously increasing. Okay. That is being considered, and very high wear we are getting against hard phase, where wear is less, but you see for cermet phase it is drastically changing. Okay. You can say this is one order of change we have. Okay. If you go for ceramic body to cermet body. Okay. That can be considered on the basis of their hardness, because our ceramic composite itself is having hardness around 24 GPa. Okay. And counter body is having 14 GPa. So that reflects here. So friction is not at all related to wear. Friction is entirely different. Friction we are getting highest for cermet, but wear we are getting highest for silicon carbide. So it is not at all related. Okay. Then we try to analyze the surface. What we found here is for silicon carbide ceramic. Okay. Be focused, it is not for tungsten carbide incorporation. For silicon carbide, if you go with 5 Newton to 10 Newton to 20 Newton, mechanical fracture and grain pull out is dominating. Okay. And if you go with the tungsten carbide particle with changing the load, we can see some debris or some embedded debris are there. Okay. And at the same time, if you go for steel, it is having some, this is adhered layer actually. Okay. This is adhered layer on the surface, at the same time abrasion is there. Okay. So this is how mechanism is changing. So this mechanism has been actually wear mapped. So with respect to load, so what we found here is, if you go with steel tungsten carbide SiC, with respect to change in load, we are getting, in case of steel it is embedded debris, which is deep grooves and mild abrasion it is moving to. Okay. In you go for cermet, it is for mild abrasion, then deep grooves, again embedded debris, in both the case of steel as well as cermet. But if you go for hard surface SiC, we are getting mechanical fracture which is getting dominated continuously with increasing the load. So in case of mechanical, in case of counter body ceramic silicon carbide, that is ceramic, we are getting more domination of, see, once we are performing any tribo test, we are having almost like 3-4 mechanisms continuously running. Okay. We have to deal with the dominant wear mechanism. If you can reduce the dominant wear mechanism, automatically you can reduce up to certain level the wear, okay, up to certain level of friction. So we are focusing here dominant wear mechanism. So in case of ceramic, with respect to ceramic, we are getting dominant mechanical fracture. In other case, we are getting some tribo layer over the surface. Okay. Then we try to analyze the worn surface of composite now. Earlier it was for monolithic SiC. Now if you incorporate tungsten carbide, okay, 10%, 30%, 50%, how it is changing. So if you see at 20 Newton now, in severe condition we are considering. So mechanical fracture is dominating, but you see mechanical fracture is getting reduced. So it is like, okay, whatever the fracture is occurring, we already have seen that fracture is getting bridged by tungsten carbide particles. Okay, they are not propagating at faster rate. So fracture is getting reduced, you see, and this fracture is somewhat cut. Okay, it is not grain pull out as well. Okay, so it is transgranular fracture is occurring. So that fracture is not at the faster rate once you incorporate tungsten carbide up to 50%. The same if you go with tungsten carbide, that adhered layer you see now it is very clear. So in case of SiC, pure monolithic SiC, it was up to somewhat it is embedded debris, but now it is continuously increasing, and we can see dominant adhered layer, because this is tungsten carbide cobalt ball. At the same time, we are increasing the content of tungsten carbide. So the cohesive force will increase. You understand the point? In case of SiC, SW0, tungsten carbide actually in the matrix is not there. So we are having some tribochemistry playing role, and embedded debris we are getting on the surface. But as you move towards incorporation of tungsten carbide to 50%, now we are seeing some adhered tribo layer over the surface against tungsten carbide, because this counter body is also tungsten carbide. Inside the surface also we are having tungsten carbide. So this will lead to more cohesive force, and that will go for more surface on the surface. Okay. Now if you go for against the steel, we are having some adhered surface, and it is continuously we can see we are having some less amount of this, but how can we confirm whether it is tribochemistry still there or not? That can get confirmed. So this is what is replicating our performance as well. So first we will talk about the wear map. So what we got the wear map as steel, tungsten carbide, SiC. Again the mechanical fracture is there, it is getting reduced. It is moving towards polishing now. Okay, if you change the content of tungsten carbide. In case of tungsten carbide, embedded debris now severe abrasion, and it is moving toward adhered oxide compacted layer that we already have seen. Similar in steel, mild, and we are seeing mild abrasion up to this particular level, you see. Okay, but once you try to analyze the ball surface now. So in case of SiC, you see we are having complete mechanical fracture, polished surface, means no tribo layer is there. You come here in tungsten carbide, cobalt ball, cermet ball, we can see some layer is forming. Okay. So that whatever tribochemistry we are analyzing over the surface of SiCWC, the same we can see over the counter body. The same is not replicated if you go for steel, but it is very much clear here. So this confirm that in case of steel also we are having increased amount of tribochemistry playing role once you go with the more amount of tungsten carbide content. Is that clear to everyone? Then we will see one surface like, okay, how debris is analyzing. So we try to analyze the debris. In case of as we have seen here, so I could have told there only. So you see our grain size is continuously decreasing. The same is getting reflected if you go with this our debris analysis. So, in case of SiC, monolithic SiC, grain size are, debris size are larger as compared to if you go for HW50, but we are not able to see any layer surface, but continuously the debris size are getting reduced, just because the larger grain size is getting fractured, smaller grain size is getting fractured. So, we are having smaller debris collected. Once if you with the we try to analyze with through the debris, and further we try to analyze with through debris only to understand what are the byproducts are forming. So, we perform Raman analysis. What we found, the debris collected against SiC, we are having formation of byproduct is tungsten oxide, silicon oxide and SiC. Obviously, it is getting rubbed. If you go with this tungsten carbide cobalt, we are having cobalt tungsten oxide, silicon oxide apart from SiC. So, that we have not seen here. Okay. Now, if you go for steel, here it is very careful, which will confirm why in case of steel actually we are getting increased amount of friction. So, byproduct forming is FeWO4 and COWO4. Okay. With increased amount of, if you go with the tungsten carbide, with increased amount of tungsten carbide, this formation will increase. Yes, and they are having high hardness as compared to steel. They are having high hardness as compared to steel. So, now they will abrade. We understood, like, okay, if you go with the harder coating, they will abrade, friction will be more. So, in case of if you go with the byproduct itself which is forming, that is harder to the surface, harder to the counter body. So, it is not only related to matrix and the inclusion, it is also related to what byproduct is forming against what counter body you are performing. Okay. So, there it is confirming, like, okay, formation of this particular byproducts actually helping in increasing in frictional behavior if you go with the steel, because these byproducts are having less hardness as compared to tungsten carbide cobalt ball and silicon carbide ball. Are you understanding? So, whatever this silicon these byproducts are forming, they are having less hardness as compared to tungsten carbide cobalt ball as well as silicon carbide ball. So, they will not play that particular role. So, continuously this is getting decreased, but if you go with the steel ball, it is continuously increasing, because that formation will increase with incorporation of more amount of tungsten carbide. Okay. Then we try to simply make it a schematic. So, if you go with monolithic SiC with all the counter body, larger grain size, we are getting more wear. As you reduce the grain size, the amount of against SiC ball, it is less amount of wear we are getting. Against, like, this is for SiC WC composite, let us say it is W50. Okay. Then against tungsten carbide ball, we are getting some tribo layer which is getting reflected here. Against steel ball, we are getting some tribo layer form which is getting reflected at counter body. So, we need to analyze the mechanism. If you try to understand, it is not only the surface we are analyzing, what is the counter surface, that we also need to analyze. Sometimes it is not very clear with the surface. If you see the silicon carbide surface, it is not showing any indication of tribo layer, it is not showing any indication of tribo layer if you see here. Yes, against steel ball, but this is getting reflected once we are analyzing the counter body. Okay. So, it is very important to understand, like, okay, it is if you want to go for what is dominant wear mechanism, we need to analyze both the surface. Then another, now the change in configuration we will see. Okay. How change in configuration will affect. So, change in configuration means it is not continuous sliding, we are going with reciprocating sliding with some stroke length. Okay. So, this is what the parameters have been chosen. So, this load due to some constraint here, this load has been chosen close to that whatever the load we have chosen for previous sliding wear condition, 5 Newton, 6 Newton, 10 Newton, 9.3 Newton, 20 Newton, 19.3 Newton. It is constrained with the instrument. Okay. And then very interesting point here is humidity. Humidity is now moderate humidity. Now, it is changing from 25 plus 5 plus minus 5 to 55 plus minus 5. Okay. So, this is being considered as moderate humid condition. It is not high humid condition like 70%, 80%, but it is moderate humid condition. And further it has been performed at 500 degrees Celsius as well. So, what we found here is again that friction is continuously decreasing with load, at the same time it is least for SW50. This is the same, but very interestingly, if you can recall here, yeah, it is here. So you see this, we are performing at against SIC only. So what we are getting, the highest amount is 0.4 and it is getting reduced up to 0.39. But if you go for moderate wear condition, and when we are changing the configuration, now whatever debris is forming inside, it is getting intact for longer duration, and debris to counter body contact time is increasing. You can understand, because here once we are moving for complete surface, debris in contact, and we are coming out again, debris is coming in contact once you are reaching to here. But once we are going for reciprocating, contact time is increasing with the debris, with the counter body. This is what is actually reflecting, because we are getting hard surface at debris. So this friction is getting increased. So this is what we are seeing, friction again getting increased because of that hard debris in contact. Okay, friction is increasing. Whether it will reflect in wear as well, that we'll see. So this is what the wear behavior we got. You see, unidirectional condition always wear is higher as compared to reciprocating, because whatever debris is forming in contact actually is getting intacted inside. Okay, and since they are for longer duration with the counter body, the debris size also getting reduced. Debris size is also getting reduced. Now in this particular humid condition, I told you, now we will see the effect of humidity. In this particular humid condition, if it is dried condition, SiC is getting converted to silicon oxide. That is what we got in Raman analysis. Okay. But if you are having better humid condition, or let us say high humid condition, again this SiO2 reacts with moisture. Okay. SiO2 reacts with moisture and it is forming silicic acid, that is SiOS4. Okay. And this is getting adhered on the surface, it is making a layer, and you see this is for unidirectional, this is for unidirectional. We are simply seeing reduction in debris size. Now by changing the configuration, you see the debris size for SW0, debris size is decreasing. Okay, debris size is decreasing, and this debris size should decrease even further for SW50. Once they are increasing further, what they are doing is, actually they are very small in size, surface area increase, they try to get agglomerate with each other, they try to get connected to each other, and with this particular humid condition, formation of this is actually leading to a cylindrical debris formation. This is leading to a cylindrical debris formation. Now even though it is rolling on this particular ball, but it can roll now, it can roll up to some extent here. So this is what is leading to, you see, very drastic change in wear. Though the friction is higher as compared to unidirectional, but in reciprocating wear is less. So this configuration plays very important role. How the debris is getting intacted, what is the environment, okay, what is the size, because you see already this debris size are getting decreased, this is getting further decreased by changing the configuration. This is getting further decreased. Now it should get further decreased for SW50. When it becomes even smaller, they try to get connected to each other, and they are forming a rolled cylindrical debris, which is actually rolling on the surface. Now they are reducing the load, as well as if you see the friction. Friction is decreasing from SW0 to SW50. So it is decreasing friction as well as wear once we are forming this cylindrical debris. Okay. Now the same thing, if it is actually effect of humidity or what, we perform the same test at 500 degrees Celsius. So what we found here is, you see at 500 always wear is higher, and in case of very drastically, if you see here, in case of SW50 it is very high. Okay. And this, the reason could be like, if you see here, because if you this surface, you see fracture surface I have shown you. So fracture surface is dominated with the transcontinental fracture, but at the same time you can see some agglomeration of tungsten carbide particles now. So if you increase the number of like amount of tungsten carbide particles, they will try to agglomerate, and that can become a stress reserve point, defect site as well. Okay. So if you increase the temperature, that thermal mismatch will lead to higher stress. This is what playing role here in case of SW50. Now it is decreasing continuously up to SW30, but now it is increasing. Okay. And at the same time we can see here that formation is not there. If you look at the surface, this is at room temperature, we can see that intacted layer, but here we are seeing completely fractured surface that can be analyzed from here as well. This is at room temperature at 500. You see there is no cylindrical debris formation. So that cylindrical debris get formed once you are having humid condition. So humidity also plays very important role. Configuration also plays very important role. Temperature also plays very important role. Okay. Grain size also plays very important role, because the grain size is decreasing, debris size is decreasing, and if it is decreasing at a certain level, they will try to connect each other and they will form a cylindrical debris, or they will go for even spherical shape and that can roll. So if the debris size is very small, that can drastically change your friction and wear behavior. Okay. So grain size also playing very important role, and that get validated. So initial, if you see, we are getting tribo layer, we did not validate, but this get validated with Evans model very well, where we are considering this, where we are considering completely mechanical fracture only, no tribo layer. So it is validated with this particular model as well. Yeah. So we'll talk. This is conclusion. We'll discuss. First, we'll see the micromechanism. We are running short of time. So micromechanism, if you see now, so we started with against the silicon carbide ball, we saw mostly it is mechanical fracture. So we did the we cut the surface using FIB, and we undeformed surface when it is not getting worn, we see no any affected region here. Okay. And the worn surfaces also, we simply cut the surface. What we can see here is now some affected region up to 1 micrometer for monolithic SiC, and this affected region is getting reduced in case of SW50. So tungsten carbide phase is actually reducing this. At the same time, we can see this generation of crack, which is getting bridged by this tungsten carbide particle, and it is not able to reach up to the surface. Okay. So it will not lead to fracture the surface. So this is how cracks are getting bridged with the tungsten carbide particle that we have seen on the surface as well, that we can see beneath the surface as well. And this radial crack and median crack, which is actually a replication of if you replicate it with the sharp indenter. Okay. In case of sharp indenter, we are getting radial and median crack. If you in case of blunt indenter, we are getting conical crack. So this radial and lateral median crack we can see here. Okay. Then we took the we prepared one TM sample out of this particular subsurface. So this is TM sample surface has been prepared. So what we can see here, if you see the phase boundary, okay, particle boundary, so the crystalline grain boundary we can see. So we have taken region 1, 2, 3. Okay. So in region 1, if you see, we are having very well crystalline surface. In region 3, you see very well crystalline surface. But if you go for that phase boundary, that is also well crystalline. Okay. So we can see here we are not having any amorphous phase in between particle and SiC. Particle and SiC is not having any amorphous phase, which lead to dominance of transgranular fracture. You see, if our grain boundaries are weaker, it will be going through intergranular fracture. But with incorporation of tungsten carbide, what we are getting here is well crystalline surface, which is leading to transgranular fracture if you go with more amount of tungsten carbide particle. Further, we try to analyze the what we have already understood with the SU formula, SU theory. Okay. So dislocations are getting generated, stress induced dislocations are getting generated, and this stress induced dislocation, they are getting piled up. You see here at the top, it is getting piled up, it is getting piled up. Okay. And this leads to crack formation. So what we have seen, like Su is saying, with continuous rubbing, it is getting deformed, dislocations are getting generated, they are getting piled up, up to some at any inclusion region, and then they are generating surface, void. Okay. They are generating two surface. So those cracks we can see here, you see formation of cracks. Okay. This small cracks. So these cracks are actually, we can see it is getting generated out of this particular dislocation forming during this reciprocating or continuous sliding condition. And confirmation of this, we can say, we can understand, like, okay, maybe we are sintering this surface, we are having tungsten carbide and SiC, it could be thermal induced stresses. Okay. It could be thermal induced stresses. So yes, we can consider these stresses as thermal induced stresses. But if you look at this particular type of thermal induced stresses, these dislocations. This is actually being considered lane shape. Lane shape comes once you are applying, once you are getting stress induced dislocations. So, this is very important to understand that dislocations are you are getting it. This dislocation line, if it is straight, you can consider it a thermal induced. Okay, thermally induced stress is there, and we are getting dislocations getting generated. Okay, but if it is stress induced, you will be having this lens shape structure. Okay, this lens shape structure which is coming out of wear. Once we are applying the stress, it is coming out of wear and it is forming, and at the same time we can see that twins are forming, and this twins in SiC, you see SiD pattern has been taken here. So, for tungsten carbide we can see it is completely crystalline surface, but if you go for SiC we can see these twins over the grain boundary, double spot, double dot. This confirm that we are having formation of twins over the grain boundary, grains of SiC, and that can again get confirmed. We have opted for this particular region, okay, which can we are considering as let us say twins. So, again we selected this, we bifurcated in 3 region 1, 2, 3. First region it is coming as 1, 1, 0. Third region you go, second region you go, second region is coming as 1, 1, 1, and again third region is coming as 1, 1, 0, 1, 1, 1, 0. So, it is like, you know, like once we are having twin formation, it is mirror like structure. So, this is what we are getting here. This is getting confirmed by if you are going for IFT analysis, okay, at high level, HR resolution level. Okay. So, this is conclusion. This last one only I am going for, like whether it is changing with sliding load and time. So, here SiC we started with a small amount of additive, that is 3% and 0.2%. We will compare this. So, just 10 minutes. Yeah. So, here we will compare 3% yttria addition as additive. Now, it is not as a composition, it is as a additive to close the pores while performing the liquid phase sintering, 3% and 0.2%. What we got here in 3% it is equiax grain, in 0.2% condition it is somewhat elongated grain, okay, bimodal grain or elongated grain, means some grains are, you see, it is elongated. This will help in generation of debris, we will see. Okay. Again how microstructure is playing role, we will see here. So, this is SY3, more amount of additive, more amount of additives we opted, more amount of additive. You see the fracture surface of SY3, okay. It is having agglomeration of yttria over the surface. So, this will let us know like, okay, why. So, this is the fracture surface, mixed mode of fracture toughness we can see, okay, fracture mixed mode of fracture, where we can see some at some stages it is grain pull out and at some stages it is grain fracture, okay. But if it is getting dominated, if you go with less amount of additives, okay, it is dominating because this yttria is going on the phases, on the grain boundaries to close the pores, but at the same time it is weaker zone, at the same time it is weaker zone. So, it will fracture the surface, the crack will propagate through this. So, this is why in case of SY3 we are getting mixed mode, in case of 0.2% this is dominating, transgranular is dominating. Okay. Then mechanical properties, if you see mechanical properties, again weaker hardness is increasing because this softer phase is less, harder phase is. So, it is obvious. At the same time fracture toughness is somewhat close to each other, flexural strength is this. Okay. And then we perform sliding wear against SiC counter body and tungsten carbide counter body. So, these are the different parameters. Okay. So, first we will see for tungsten carbide counter body, what we see, okay, again it is lower for 0.2% and higher for 3%, and wear is also higher for 3%, lower for 0.2% everywhere. Okay. But very interestingly we will see here the surface, you see it is completely fracture and embedded debris are there. Okay. And accordingly we are getting, in case of 3 agglomeration of particles are there. So, it is leading to higher fracture and higher material removal. Okay. Debris analysis also shows, if you see the fracture surface for both at 5 Newton and 10 Newton, we can see here debris size is only getting reduced, okay, in both the condition, but the dominant wear mechanism we are getting here as mechanical fracture. So, this again get validated because it is mechanical fracture, no tribal layer we saw here. So again it is getting validated through Evans model, because it is forming the cracks, like we already have seen SIC, it is radial and median crack. So it is following to, it is validating to, very well validating to our Evans model, where we are considering sharp indenter fracturing the surface. Okay. So these are the key findings here. Then once we are moving to SIC, it is very interesting. Again the fracture surface. In case of SY3, I am directly going to one surface. So it is in case of SY3 it is fractured surface, but in case of SY.2 we are seeing some adhered, strongly adhered layer. Okay. And this is again the chemistry, we can understand. This chemistry we can see here. Now with as a function of load, if you see, for SY3 it is continuously fracture, it is getting smaller in size, somewhat cylindrical debris is forming. But once we are having less amount of additive, with increasing load, more formation of this cylindrical debris, which is leading to more reduction in wear and friction with increasing even load. Okay. And the same time, if you go with time, now this debris, cylindrical debris is forming against, it is for 20 minutes, has been run for 20 minutes. So it is forming for 0.2. So for 0.2% yttriac with SIC we perform with time. So what we got here with time also, you see initially it is very fine debris we are forming, which are getting connected with time, and ultimately it is forming cylindrical debris. So very, if you generate very fine this debris, you if you compare 0.2%, the debris are actually large if you go with the 5 Newton. If you increase the load, if you increase the load for 20 Newton, so these debris are getting finer, and then with time it is getting connected, and ultimately it is forming a cylindrical debris, which is actually evaluating your complete frictional behavior. So if you are going for a scratch test, sometimes we are performing this tribo test as scratch test. In one go you will be getting that particular behavior. So you will not be able to understand whether it is actually performing you the, giving you the actual result. So ultimately if you go with the passage of time, you are getting more cylindrical debris. So for long run it can be very beneficial, for short run it might not be very beneficial. Okay. So this is how we have to analyze the surface. So key finding from here, like mechanical fracture is equiax for SY3, and it is tribochemical wear is dominate once we are going for SIC counter body, okay, in SY02, and it is adult tribochemical release responsible to reduce in friction and wear for SY.2. Okay. So this is overall conclusion we have. It affects, it get affected by counter body, it get affected by sliding load, configuration, temperature, humidity. So it is not only we can talk like with the amplitude of stress, okay, and then load level. It depends on materials property and in what environment, what configuration you are using. Okay. Then overall, if you go for fatigue wear, condition for wear, material level approach, you can go with grain refinement. Okay. And then phase stabilization, because phase is more stronger, it will be, if it is stable on the surface, it will reduce the wear. Composite design you can go according to improvement in fracture toughness, and it will give better wear property. And then material chemistry we have to look at very carefully. And design level again, the geometry you have to optimize, whether debris are getting out of the surface or getting injected inside the surface. Okay. And then load management and quality control, always it is there. Thank you. Any question? Bimodal grain means it is having somewhat, you say, elongated as well as equiax, this one. So this is equiax, means you see it is in all the direction, it is going almost same, but here it is equiax, means these are equiax, but these are elongated. So this is bimodal grain. If it is continuously all are elongated, we will see elongated grains, but it is having mixture of elongated as well as equiax grain, that is bimodal grain. Where? Yeah, yeah, this one, validation. Here we are comparing with R square value. If R square value is more than 0.9, we consider regress value. Okay. So if it is, yeah, so that's what actually, if you go with all the values, if R square is coming more than, that's what we are getting. Yeah, yeah. This is actually volume you are telling. This both are volume. One is computed, one is experimental. Yeah, yeah, yeah. Yeah, yeah, it is only the parameters that 10 to the power minus 3 and 10 to it is directly mm cube. It is following that linear, like linear. No, no, it is not equal. This is what, it is not equal always. This is validation. No, no, it is not validated through this one actually. It is validated through the method it is being used. So if it is getting the values in this particular rate of change, the same we are getting once we are performing the experimental. But experimental, you know, like this validation is like once model is being proposed, it is only on the basis of E, H, all those values. Okay. But if you are going for experimental, we have to go with different number of variables, okay, which is being considered. If you go from the from laboratory scale to higher scale, we are usually going with, you are working with fluid dynamics, Reynolds number, other like unitless number. Okay. So it is only to compare, like, okay, because these all parameters we cannot replicate at the same level. So the similar has been done here. This model is only considering hardness, fracture toughness, and all those things. But other parameters, like you say their structure, grain boundary, and all those things are also affecting. So this is what coming. The rate of change is same. It is close to that. This is what it is. It is not the value. It is actually validated. See here also we validated. You see, it is close to that, but this value is not the same. Okay, rate of change of this wear is should be in the same pattern. Any other question? I think he is. No question. Thank you. You can start then, sir. Yeah.